Hi everyone, it's Mr. Barden here. This video I'm going to be going over just, well, as you can see on the screen and from the thumbnail, just some of the basic concepts of how sound works and how synthesizers work for my sound design course. So this isn't going to be a super in-depth deep dive into everything, more so just a cursory overglance over the more important concepts needed in order to start working with synthesizers and generating audio with our programs and DAWs that we use. So, with that being said, let's just hop in. And as we're going, if you like or enjoy the video, please, comment and subscribe and all the YouTube stuff. But if you have any questions about anything I say, definitely put those down in the comments. I love seeing people reach out and ask questions and go from there. So, what is sound? Well, sound is it's vibrations, things vibrating. That's really all it is. Something vibrates. Usually, your voice or a speaker of some kind in our modern days, and then those vibrations travel through the air or whatever until we can hear them. One fun little trick to do is if you just kind of lightly place your fingers on your throat as you're talking, usually kind of right in the front middle area right here, not like you're checking your pulse, but more in the front, and just say stuff, you'll actually hear your voice, your vocal cords vibrating. Now again, don't like choke yourself, but you just lightly place your fingers there, you'll be able to feel it. Um, Okay, so these vibration sources can come from anywhere. It can be whatever. I mean, I'm sure you've heard, cars make a noise, your dog or cat makes a noise, people make noises. Uh, it doesn't matter what, as long as it's creating these vibrations that can then travel to our ears so we can hear them. That's really all sound is at the core level, is just moving vibrations that our brain thinks about. Okay, as for how this sound travels, uh, I have some diagrams spread out through here that'll make this a little bit clearer, but basically, whatever the sound source is, vibrates. This causes the molecules of air or water or whatever's around the sound source to vibrate as well. So it'll kind of push one molecule back and forth, and it'll bump into the one next to it, and that'll cause it to move. Then it bumps, and they keep bumping, and so on and so on and so forth, until it finally reaches our ears, and then the brain can interpret that as sound. Here's a little bit of a diagram to go with that. So you can see here's the speaker, and as that vibrates, that causes the molecules to kind of get pushed, and they kind of bunch up, and then they all spread out, and then that causes the next ones to bunch up and spread out, and so forth, causing these waves of high and low pressure to travel through the air, and that is sound. We often illustrate this with the waveform diagram here, where as you move up in the vertical space, you're indicating higher pressure, and lower is, well, lower pressure, and so forth, with being right in the middle being a true kind of neutral element in terms of pressure. So that's what's happening there. The actual molecules are not traveling from the sound source to your ears. That's not what's happening. Again, the molecules here are moving kind of like this. They're bouncing into one thing and moving back and bouncing. It's bouncing back and forth, and it's just transferring the energy through the air, not moving the molecules themselves all that way. Okay. So, as I mentioned, we have that high and low pressure, and that causes this kind of repeating pattern of, well, the pressure. When that hits our ears, that is what we are interpreting as this high and low pressure difference in our ears. And pretty much the higher, the more quickly, the higher the frequency of this pressure difference that enters into our ears and goes to our brain, that's what perceives the pitch. So as a low noise like this is alternating between high and low pressure a lot slower, than a high noise like this. We'll pretend I, didn't sound moderately terrifying doing that, and could actually hit high pitches like on my keyboard. But that's the idea, is that your brain knows that the more quickly it's alternating between high and low pressure, the higher pitched the sound seems. And I'll talk about how the brain knows that in a little bit. And then this one, if I didn't mention it, I'd be remiss, but I think it's kind of intuitive, and that is that the more intense the waves, the bigger the waves are here. So the more pressure, the greater that differential, the louder the sound seems. So again, that's just more energy equals more loud, and that's called the amplitude. Okay, so here I've got some, very, very high resolution photos, but they're showing, kind of a lot of what I've talked about, but with a little more in depth labeling than I've gone to. So again, we've got the same diagram here, but everything's kind of labeled so you can see, okay, here's the compressed air, here's the, well, it's called rarefaction, but the spread out, less dense air, and how everything's lining up between the two diagrams. Over here is just kind of showing what I mentioned, where the more times it goes between high and low, the higher the pitch, and then the higher the amplitude, the louder the sound. So again, that's just kind of illustrating that visually. So one thing that's important to note is that without some medium to travel through, again, it's usually air, but not always. Sound cannot exist. Again, it's reliant on molecules of some kind of material bumping into each other and transferring that energy until it hits our ears. This speed varies, and I've got a chart here from the sound unit in my coding textbook that is kind of illustrating this interesting phenomena we see, and that is that the denser the material, the quicker sound travels through it. Now, that being said, it also can die off quicker, so it may not travel as far, but the distance that it travels, it will do that much more quickly in a denser material. And this is because just the molecules are closer together, so that way they don't have to travel as far before they hit the next one and transfer that energy. But a little bit of energy is always lost every time that happens, so that's why it may not travel as far, but it'll travel quicker. And I've just got some of these listed out right here. For my classes, I don't really make them memorize it. It's important that they kind of have an idea of what the speed of sound in air is. But for what we're doing in this audio production class, you really don't need to know that, it's approximately 1580 meters per second through muscle and stuff like that. That's not quite what we focus on. Okay, speaking of muscle and body parts, let's just talk about the ear real quick. Um, so there's a lot of text on the screen, and I'm actually hiding some of it, so I'm gonna do this and remove my face from the screen for just a moment. Uh, so basically, the sound will travel through whatever medium. It has to travel through something. That's why there's no sound in space, because it's not dense enough for the sound waves to travel. But it'll go until it gets picked up by our ears. Otherwise, it's just radiating out forever. No one can hear anything until it reaches their ears. The part of your ear on the outside called the pinna, and I'll have diagrams for this on the next slide, don't worry. That's kind of like a satellite dish in the sense that it's out there outside of your head. Most of your ear is inside of your head. This little fleshy cartilage bit that you see is used to pick up these incoming sounds and to kind of funnel those vibrations into your inner ear. So it's a very useful thing. Without it, you wouldn't be able to hear nearly as well. A little side note, you'll notice that your ears are actually facing forward a little bit, so people hear more from the front, which again makes sense. You want to look at something and hear what's going on. Uh, so you'll notice a lot of high-end headphones. I'm going to bring my camera back for this. A lot of higher-end headphones will actually swivel just a little bit to accommodate for the fact that our ears don't face out, they face forward. Um, and then they'll swivel to varying degrees based on different people. But that's one way you can tell, just kind of at a glance, whether or not a pair of headphones is decent or not. There's other stuff, but I just wanted to kind of go off on that tangent. Okay, so once the vibrations hit the pinna and get funneled into the inner ear, we find the eardrum, or sometimes called the tympanic membrane. I think eardrum is easier to say, so I'm going to use that during this presentation. But basically, it's like a small, stretched flap of tissue in your ear. If you poke in it with a Q-tip, you could break your eardrum. So that's why they tell you don't poke in your ears with a Q-tip. But basically, this acts very similarly to a drum head. In fact, if you were to go after watching this and just Google, vibrating drum head, you'll see how that works. But as those vibrations go, it'll vibrate that membrane back and forth, and then those get picked up by a few small bones in your inner ear that then attach to an organ called the cochlea. This organ is curled up and full of little sensory organs and fluid. And then various frequencies will stimulate various portions of the cochlea. So it's acting kind of like a filter. So only certain frequencies can travel to certain areas. Um, and then those will stimulate those sensory organs, which then send the signal to the brain, which then tells the brain how to interpret the sound. Different sensory organs tell the brain what frequencies to that it is. So again, certain ones only get stimulated when higher sounds happen. Other ones only happen when lower sounds happen. That's how humans can tell them apart. And then how much stimulation occurs just tells the brain how loud or soft the sound is. There we go. So I've got a diagram of it here, but before I do that, I want to just pick up off of what I mentioned about the loudness of the sound, and that is that you can damage your ears by listening to sounds that are too loud. I'm not going to go into all of that, but basically, if you have extremely loud sounds or, significantly loud sounds over a long period of time, it's recommended that you wear earplugs, take your headphones out, go somewhere else, just to give your ears a break. You can damage your hearing by exposure to very long, loud sounds. And that's usually, somewhere around 100 decibels is kind of that threshold of pain. So, there's resources on that. I'm not going to go too much into it because for this class, that as long as you're following my instructions, won't be a problem. Anyways, tangent done. Here is a diagram of the human ear. Again, this part, the part we normally refer to as the ear, is very little of the whole thing. So again, the sound waves come in, they go through this canal until they hit the eardrum right here, and then it gets picked up by these bones. There's three of them. You remember the hammer, the anvil, and the stirrup was what I remember them being called when I was in school. But then from there, it enters the cochlea, which is this curled up thing. This diagram doesn't do a great job of showing the curling. In actuality, it looks kind of like a snail shell from there. But inside, there are all of these little sensory organs and fluid and then it'll send the nerve impulses to the brain. Here's a more accurate one. Again, it's more curled up, but in reality, it's tighter. They've made room for these labels, but you'll notice that various frequencies are stimulating different portions of the organ, and you can kind of see what that looks like here. So, high frequencies kind of get fed out here versus the medium and low frequencies travel further along the diagram. So that's how we can hear different frequencies. Any questions so far? I realize this is a pre-recorded video, so if you have any questions, put those in the comments and we'll go from there. I'm also going to give this lecture to my students, so I factored in a place for questions. Because we are moving on to something different, that being how a synthesizer works. So, a synthesizer, it's a sound source. It generates sound. Generally, we generate these vibrations, but A synthesizer is going to generate its sound signal electronically. That's what it's doing. It's not like an acoustic instrument like a guitar or a clarinet or a trumpet or things like that. All of this is done electronically. So instead of generating physical vibrations that move between high and low pressure, it instead oscillates between high and low voltages of electricity. So we still get this, high and low cyclic pressure phenomenon happening. It's just instead of it being air pressure, it is just electrical voltages instead. By changing that specific pattern that the synthesizer takes to move from high to low voltage, we can change how the sound, sounds. These are called waveforms, and it's very straightforward. I've got this diagram here that again is 4K image, um, but these are the kind of the four basically recognized images. It's an image of the four basically recognized waveforms. There's sine, which again has a smooth gradient from high to low voltage. Square just jumps immediately from high to low. Triangle is kind of like sine, except we move linearly instead of with this curve applied. And then sawtooth is like a combination of square and triangle. I'm not going to do it here on this video because of YouTube and copyright and all that, but if there's going to be a link to these slides in the video, and I'll give them all to my students, but if you click on this, it will take you to another YouTube video that will illustrate how these all sound different. So definitely check that out afterwards. We're approaching the end of my video here. Okay, as for that, basically what we can do is once we generate that signal, we can then send it to something called the digital to analog converter. I realized I called it the wrong thing as I was saying that. It's the digital to analog. I'll fix that after I'm done talking. But once they've been generated, we can send them to that digital to analog converter, send that out to the speakers, and we can hear it. But there's other things we can do in order to customize and get exactly the sounds that we want. The first thing we can do is combine a bunch of sounds together. And by layering these different sounds, we can make a unique sound that's a timbre, it's a French word, a unique tone quality by combining these different waveforms together. The opposite is also true. We can start with just pure noise or a more complex sound and remove certain frequencies and waveforms to get a desired sound. The other thing we can do is to alter that waveform with audio effects. Now, I'm not going to go into a lot of detail about that because that is its own topic. It'll be its own video. Don't worry, that will be coming. But basically, what we can do is either with a hardware circuit, like a hardware synthesizer. If you've played electric guitar or similar instruments before, they have these foot pedals that you can plug into. Those are just little circuit boards that alter the electronic signal that's getting sent out to the amplifier and the speakers. We can do that too with our digital audio workstations, although instead of being hardware circuits, these tend to be computer algorithms that alter the digital circuits or the digital voltages in order to change it before it gets converted to an analog signal. So we have a bunch of complicated math that lets us do things like distortion and reverb and EQs and delay, and I'm kind of running out of ideas off the top of my head, but any audio effect that you can work with in a DAW is just a very complicated equation that changes what the electrical and computer values of these signals are in the computer's memory before we convert them into actual signals that we can hear. All right, so that is pretty much it. Again, this is just a basic overview of what sound is, how it works, how we hear it, and specifically how a synthesizer works. Again, we generate those voltages and then send them out to the to be heard. Most synthesizers have either built-in effects or are designed to, be run through various other effects to customize the sound. I'm going to be bringing in a synthesizer in a few days just to show that off after we've got a little bit more experience in my class with working with the software synthesizers and the effects, and going from there. So that's going to be it from this video. Again, if you liked it, subscribe, uh, like all the stuff. If you have any questions about anything that I talked about and want a further explanation, definitely put that down in the comments, and I will respond to those as soon as I get a chance to. So that'll be all, and I'll see you all the next time that I see you. Bye.